Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the 11th week of this massive open online course on Sociology of Development. As you know, we have covered 10 weeks of this course. In the first week, we have discussed historical location of the idea of development. In the second week, we have discussed decolonization, rise of nationalism in the third world, and the desire for development. In the third week, we have discussed classical sociology and the notions of social change. And in the fourth, fifth, and sixth weeks, we have discussed modernization theory. In the seventh week, we have discussed critics of modernization theory. In the eighth and ninth week, we have discussed dependency theory, and in the last week, in the 10th week, we have discussed critics of modern dependency theory. And from now onward, what we are going to do in the 11th week, in this week, in terms of 3 lectures, we are going to discuss limits to growth thesis. And when I say limits to growth thesis, then I'm not only trying to look at Meadows and her colleagues' works, but I'm also trying to look at Schumacher's small is beautiful and so on. Okay, post-development trajectory, and then we'll end with in the next week we'll discuss Toward a History of Needs by Ivan Illich, and then Franz J. Surman's Paradigms Lost and Paradigms Regained, how to locate development studies in general and sociology of development in particular in the 21st century. Okay, now let us start with limits to growth thesis by Meadows and her colleagues. If you look at the trajectory that we have followed from the modernization theory and its critics to dependency theory and its critics, you will find that what we are going to do now, that the limits to growth, a report for the Club of Rome's project on the predicament of mankind. The limits to growth, LTG, is shortly written, is a 1972 report on the exponential economic and population growth with a finite supply of resources studied by computer simulation. Commissioned by the Club of Rome, the findings of the study were first presented at international gatherings in Moscow and Rio de Janeiro in the summer of 1971. And the report's authors were Donella H. Meadows, Dennis L. Meadows, Jorgen Randers, and William W. Behrens III, representing a team of 17 researchers. Since its publication, some 30 million copies of the book in 30 languages have been purchased. It continues to generate debate and has been the subject of several subsequent publications. The Limits to Growth, the 30-year update, was published in 2004, and in 2012 a 40-year forecast from Jorgen Randers, one of the book's original authors, was published as 2052, a global forecast for the next 40 years. The Club of Rome, when I say, I mean it's a global think tank that deals with a variety of international political issues. It was founded in April 1968 by Aurelio Pesci, an Italian industrialist, and Alexander King, a Scottish scientist, and raised considerable public attention in 1972 with its report The Limits to Growth, a report for the Club of Rome's project on the predicament of mankind. Okay, thereby you will find there was an alliance between science and industry. Okay, what the Club of Rome suggested that the common enemy of humanity is human being. So democracy may not be well suited to the tasks ahead. However, the threat of pollution, global warming, water shortages and famines can be used to fulfill humanity's need for a common adversary. The Club of Rome was formed when a small international group of people from the field of academic, civil society and diplomacy and industry met at a villa in Rome in Italy, and hence the name appeared, the Club of Rome. I mean, Hassan Özbekhan, Eric Jantz and Alexander Christakis were responsible for conceptualizing the original prospects of the Club of Rome titled The Predicament of Mankind. What is that, the predicament of mankind? I mean, humanistic architecture and participation of stakeholders in democratic dialogue. Then you bring in a variety of stakeholders from academia, from industry, from civil society and so on, so far as so that you can have a fruitful democratic dialogue. Okay. In commissioning the Massachusetts Institute of Technology team, MIT team, to undertake the project that resulted in The Limits to Growth, a report for the Club of Rome's project on the predicament of mankind, the Club of Rome had three objectives. One, to gain insights into the limits of our world system and the constraints that it puts on human numbers and activity. Secondly, to identify and study the dominant elements and their interactions that influence the long-term behavior of world systems. And thirdly, to warn of the likely outcome of contemporary economic and industrial policies with a view to influencing changes to a sustainable lifestyle. The methodology that the authors of the LTG, I mean the Limits to Growth thesis, adopted, that the World 3 model, I mean all, first world, second world, third world, all, World 3 model to simulate the consequence of interactions between the earth and human systems. The model was based on the work of J. Wright Forrester of MIT as described in his book World Dynamics in 1971. That simulation, when I say, I mean the models were run on Dynamo, a simulation programming language. LTG, the Limits to Growth thesis, echoes some of the concerns and predictions of Malthus in his book, An Essay on the Principle of Population in 1798, where Malthus argued that our resources increase in an arithmetic progression, whereas our population increases at a geometric progression. Okay, that's why we must use our resources in a more sustainable manner. What the authors of the Limits to Growth thesis argue that perhaps the world economic as well as world population growth, I mean world economic growth on the one hand and world population growth on the other, if you look at this, then perhaps the list of necessary ingredients is long, but it can be divided roughly into two main categories. The first category, if you look at the first category, includes the physical necessities. Okay, and the second category includes the social necessities. Physical necessities and social necessities. When I say physical necessities that support all physiological and industrial activity, I mean food, raw materials, fossil and nuclear fuels, and the ecological systems of the planet which absorb wastes and recycle important basic chemical substances. And these ingredients are in principle tangible, countable items such as arable land, fresh water, metals, forests, the oceans and so on. Okay, and that's how an assessment must be made of the world stocks of these physical resources, since they are the ultimate determinants of the limits to growth on this earth, on this planet. And the second category of necessary ingredients for growth consists of the social necessities. I mean, even if the earth's physical systems are capable of supporting a much larger, more economically developed population, the actual growth of the economy and of the population will depend on such factors as peace and social stability, education and employment, and steady technological progress. And these factors are much more difficult to assess, to predict. That's why if you want to predict social necessities, it's much more difficult to assess as compared to physical necessities. Okay, what the authors tried to do in the limits to growth thesis argument, that their world model at this stage in its development may not be able to deal explicitly with these social necessities, social factors, except in so far as their information about the quantity and distribution of physical supplies can indicate possible future social problems. That's why food resources and a healthy environment are necessary, but not sufficient conditions for growth. Even if they are abundant, growth may be stopped by social problems. Let us assume for the moment, however, that the best possible social conditions should prevail. How much growth will the physical system then support? The answer that they obtained would give us some estimate of the upper limits to population and capital growth, but no guarantee that growth will actually proceed that far. Okay, in this context, it's extremely important to understand how they went ahead with this. Before we come to food resources and a healthy environment, and which are considered necessary but not sufficient conditions for growth, 5 variables were examined in the original model on the assumptions that exponential growth accurately described their patterns of increase, and that the ability of technology to increase the availability of resources only linearly. Okay, then what were those 5 variables which were examined in the original model by the authors of the LTG? I mean, limits to growth thesis. 1, world population. 2, industrialization. 3, pollution. 4, food production. And 5, consumption of non-renewable natural resources. I mean, resource depletion. Okay. In this context, the authors of LTG intended to explore the possibility of a sustainable feedback pattern that would be achieved by altering growth trends among these 5 variables, namely world population, industrialization, pollution, food production and resource depletion, I mean consumption of non-renewable resources, under 3 scenarios. What are these 3 scenarios? We'll come back to this point. I mean, what the authors of LTG at this point noted that their projections for the values of the variables in each scenario were predictions only in the most limited sense of the word and were only indications of the system's behavioral tendencies. What are those 3 scenarios? I mean, 2 of the scenarios saw overshoot and collapse of the global system by the mid to later part of the 21st century, while a third scenario resulted in a stabilized world. Okay. In this context, it's important to understand that exponential reserve index that the authors of the LTG thesis propounded, that a key idea in LTG is the notion that if the rate of resource use is increasing, the amount of reserves cannot be calculated by simply taking the current known reserves and dividing by the current annual uses, as is typically done to obtain a static index. For example, in 1972, the amount of chromium reserves was 775 million metric tons, of which 1.85 million metric tons were mined annually. Then the static index is that 775 divided by 1.85 is equal to 418 years. Then our chromium reserves, whatever we have today, I mean we had in 1972, it will last for 418 years. Okay, that's what the static index suggests. But if if you look at this, that the amount of chromium reserves was 775 million metric tons, of which 1.85 million metric tons were mined annually. Then if instead of assuming a constant rate of uses, the assumption of a constant rate of growth of 2.6% annually is meant, then the resource will instead last only 93 years. One must understand this precisely because when the population increases, your uses of chromium, uses of natural resources, uses of non-renewable resources will also increase, right? Okay. It's not like that the consumption will remain stagnant or will decline. The consumption will also go up, right? Then in this context, as the authors accurately pointed out, the authors of the LTG accurately pointed out that if instead of assuming a constant rate of uses, the assumption of a constant rate of growth of 2.6% annually is made, then the resource will instead last for only 93 years, not 418 years. Okay. Then what is the formula to calculate this? Now, the formula for calculating the amount of time left for a resource with constant consumption growth is y refers to years left, is equal to, years left is equal to log 1 minus within bracket 1 minus g into r divided by c divided by log g minus 1. Y indicates years left, small g, okay, it refers to annual consumption growth 2.6%, 1.026. Capital R refers to reserve and capital C refers to annual consumption. Okay, that's why we discussed how, but if you look at the rate of chromium consumption, which was growing at 2.6% annually, then the resource will instead last only 93 years. Okay. When you come to commodity reserve extrapolation, the authors of limits to growth thesis listed a number of similar exponential indices comparing current reserves multiplied by a factor of 5. It contains a large table, of course, if you look at the original report of the limits to growth thesis, that spans for 5 pages in total. I mean, that table itself, based on actual geological reserves data for total 19 non-renewable resources, and analyzes their reserves at 1972 modeling time of their exertion under 3 scenarios. That's what we have discussed. I mean, it may overshoot, it may collapse, and it may lead to a stabilized world. That these 3 scenarios, if you look at, I mean, it may remain static. I mean, then the growth will be constant. Growth will remain constant, and maybe the second scenario would be exponential growth, or you can say, I mean, exponential index, exponential growth, and the third possibility, third scenario is that exponential with reserves multiplied by 5 to account for possible discoveries. In the context of chromium, we have seen how instead of 418 years, there is this such resource will last only 93 years if you not only look at how much tons, how much million metric tons are mined annually, but at the same time, if you look at the rate of chromium consumption, which was growing at 2.6% annually, okay, like this, if you look at this commodity reserve extrapolation, the authors of the limits to growth thesis, they tried to look at 5 resources in terms of chromium, in terms of gold, in terms of iron, in terms of lead, in terms of petroleum. I mean, they looked at many other resources, and just to give you an example how it went on. If you look at consumption, I mean, these are the resources. If you look at the consumption, I mean, projected average annual growth rate. In the context of chromium, we saw 2.6%. In the context of gold, it is 4.1%. In the context of iron, it is 1.8%. Lead 2%, and petroleum 3.9%. If you look at the static index only, it will last for approximately 418 years. I mean, 420 years. Chromium, for gold, it is 11 years. Iron, it is 240 years. Lead, it is 26 years, and petroleum, it is 31 years. Okay. If you look at exponential index, then it will lead, chromium would last for, I mean, if you follow this formula, then you will find that chromium would last for 93 years, I mean, closely 95 years, gold 9 years, iron 93 years, lead 21 years, and petroleum 20 years. Then the projected, I mean, the tendency, the behavioral modes that suggest that no, one may say that no, we'll go ahead with only static index because of the generation of resources, but not the consumption of resources. But the authors of limits to growth thesis suggested that no, you should not only look at the generation of resources, but also the changing dynamics of the consumption rate of consumption. Okay, that's how exponential index assumes greater significance in the context of limits to growth. Okay. then 5 times reserves exponential index, then if we say that no, mankind also knows how to generate more resources to to satisfy human needs, then even if you do that, then chromium would last for 154 years, gold 29 years, iron 173 years, lead 64 years, and petroleum 50 years only. Okay. Then the projected amount that non-renewable resources, one must try to look at this. The only problem, I mean, why both these indices, both static index as well as exponential index, are flawed ones, precisely because the static reserve numbers assumes that the usage is constant, and the exponential reserve assumes that the growth rate is constant. I mean, both are flawed ones. Okay. When I say commodity reserve extrapolation, it contains a detailed computer model of chromium availability with current, I mean, as of 1972, and double the known reserves, as well as numerous statements on the current increasing price trends for discussed metals, including, I mean, chromium, gold, iron, lead, and petroleum. I mean, what in the limits to growth, I mean, that book, in chapter 2, page number 66, what the authors wrote, that given present resources consumption rates and the projected rise in the rates, the great majority of the currently important non-renewable resources will be extremely costly 100 years from now. And the prices of these resources with the shortest static reserve indices have already begun to increase. The price of mercury, for example, has gone up 500% in the last 20 years, and the price of lead has increased 300% in the last 30 years. You look at fuel consumption today, you will find that this is the same problem. Okay. Due to the detailed nature and use of the actual reserves of actual resources and their real world price trends, the indices have been interpreted as a prediction of the number of years until the world would run out of them, both by environmentalist groups calling for greater conservation and restrictions on use, and by skeptics criticizing the predictions' accuracy. This interpretation has been widely propagated by media and environmental organizations and authors who, apart from a note about the possibility of the future flows being more complicated, and did not clearly constrain or deny this interpretation. While environmental organizations used it to support their arguments, a number of economists used it to criticize the limits to growth thesis as a whole shortly after its publication in the 1970s. For example, Peter Passel, Mark Roberts, and Leonard Ross, with similar criticism reoccurring from Ronald Belli, George Goodman, and others in 1990s. In 2011, Hugo Badi, in the Limits to Growth Revisited, argued that nowhere in the book was it stated that the numbers were supposed to be read as predictions. Nonetheless, as they were only tangible numbers referring to actual resources, they were promptly picked as such by both supporters as well as opponents. While this chapter, that the second chapter, serves as an introduction to the concept of exponential growth modeling, the actual World 3 model uses an abstract non-renewable resources component based on static coefficients rather than actual physical commodities. Given business, I mean, before getting into the food resources and a healthy environment, what very broadly what LTG concluded that given business as usual, that is no changes to historical growth trends, the limits to growth on earth would become evident by 2072, leading to sudden and uncontrollable decline in both population and industrial capacity. How? I mean, this includes 1. Global industrial per capita reaches a peak around 2008, followed by a rapid decline. Secondly, global food per capita reaches a peak around 2020, followed by a rapid decline. 3. Global services per capita reaches a peak around 2020, followed by a rapid decline. And 4. Global population reaches a peak in 2030, followed by a rapid decline. And then growth trends existing in 1972 could be altered so that sustainable ecological and economic stability could be achieved. And the sooner the world's people start striving for the second outcome above, I mean the growth trends existing in 1972 could be altered so that sustainable ecological and economic stability could be achieved, I mean the better the chance of achieving it. Okay. The most recent updated version was published on the 1st of June 2004 by Chelsea Publishing Company and Earthscan under the name Limits to Growth, the 30-year update. Donella Meadows, Jorgen Randers and Dennis Meadows have updated and expanded the original version. They had previously published Beyond the Limits in 1993 as a 20-year update on the original material. In 2008, Graham Turner at the Commonwealth Scientific and Industrial Research Organization in Australia published a paper called A Comparison of the Limits to Growth with 30 Years of Reality. It examined the past 30 years of reality with the predictions made in 1972 and found that changes in industrial production, food production and pollution are all in line with the original LTG's predictions about economic and societal collapse in the 21st century. The purpose is not to make specific predictions but to explore how exponential growth interacts with finite resources, because the size of resources is not known, only the general behavior can be explored. I mean, the purpose of the world model. The authors of LTG were interested in the broad behavior modes of the population capital system. What do we mean by behavior modes? The behavior modes refer to the tendencies of the variables in the system, maybe population, maybe pollution, maybe industrialization, maybe food production, maybe resource depletion, to change as time progresses. A variable may increase, may decrease, may remain constant, may oscillate or combine several of these characteristic modes. To determine which, if any, of these behavior modes will be most characteristic of the world system as reaches the limits to growth, this process of determining behavior modes is prediction only in the most limited sense of the word. Values for world population, capital and other variables on a time scale that begins in 1900 and continues until 2100. These are not exact predictions about the values of the variables at any particular year in the future. They are only indications of the system's behavioral tendencies only. Okay. Then in this context, it is extremely important to look at food, resources and a healthy environment, which are necessary but not sufficient conditions for growth. Even if they are abundant, I mean food, resources and a healthy environment may be available in abundance, growth may be stopped by social problems, social necessities. That's what we have discussed a while ago, that physical necessities and social necessities. Let us assume for the moment, however, that the best possible social conditions would prevail, but how much growth will the physical system then support? The answer we obtain would give us some estimate of the upper limits to population and capital growth, but no guarantee that growth would actually proceed that far. No one knows how many of the world's people are adequately nourished today. Okay, if you look at food production, but there is general agreement that the number is large. Perhaps 50 to 60% of the population of the less industrialized countries, which means 1/3 of the population of the world. Estimates, if you look at the protein and calorie intake, estimates by the United Nations Food and Agriculture Organization indicate that in most of the developing countries, basic caloric requirements and particularly protein requirements are not being supplied, and India is no exception to this. Furthermore, although the total world agricultural production is increasing, food production per capita in the non-industrialized countries is barely holding constant in its present inadequate level. Do these rather dismal statistics mean that the limits of food production on the earth have already been reached? The primary resource necessary for producing food is land. That is the fixed factor of production. There are four factors of production: land, labor, capital, and entrepreneur. The primary resource that is necessary for producing food is land. That is a fixed factor of production. Okay, labor is required, capital is required, entrepreneur is required, but these three are these three vary. Okay, but land is fixed. If you look at the studies which were carried out by the authors of the LTG, these indicate that there are at most about 3.2 billion hectares of land, I mean 7.86 million acres, potentially suitable for agriculture on this planet, on the earth. Approximately half of that land, the richest, most accessible half, is under cultivation today. The remaining land would require immense capital inputs to reach, clear, irrigate or fertilize before it is ready to produce food. And the same Food and Agriculture Organization report suggests that opening more land to cultivation is not economically feasible, even given the pressing need for food in the world today. For example, in Southern Asia, in some countries in Eastern Asia, in the Near East, in North Africa, in certain parts of Latin America and Africa, there is almost no scope for expanding the arable area. In the drier regions, it will even be necessary to return to permanent pasture of the land which is marginal or submarginal for cultivation. In most of Latin America and Africa, south of the Sahara, there are still considerable possibilities for expanding cultivated area, but the costs of development are high, and it will be often more economical to intensify utilization of the areas already settled. If the world's people decide to pay the high capital costs to cultivate all possible arable land and to produce as much food as possible, how many people could theoretically be fed? If you look at the arable land, I mean total world supply of arable land is, as I said, around 3.2 billion hectares, and about 0.4% per person of arable land are needed at present productivity. That's why the land needed thus reflects the population growth. If you look at the limits to growth thesis, you will find that it is, land loss through erosion is also significant. Okay, land loss through industrialization also is significant. Okay, it must illustrate some very important general facts about exponential growth within a limited space. First, it must show how one can move within a very few years from a situation of great abundance to one of great scarcity. There has been an overwhelming excess of potentially arable land for all of history, and now within 30-40 years or 50 years or about one population doubling time, there may be a sudden and serious shortage. A second lesson to be learned from this is that precise numerical assumptions about the limits of the earth are unimportant when viewed against the inexorable progress of exponential growth. We might assume, for example, that no arable land is taken for cities, roads or other non-agricultural uses. In that case, the land available is constant. The point at which the land availability of land on the one hand and population growth on the other, if you find that the point that we can suppose that it is possible to double or even quadruple the productivity of land through advances in agricultural technology and investments in capital such as tractors, fertilizers, irrigation systems and so on. The effects of two different assumptions about increased productivity, one can look at the productivity if you look at for example green revolution and then gene revolution. Obviously productivity increased in the context of green revolution, but it also brought in certain regional imbalance between agriculturally developed regions on the one hand and agriculturally underdeveloped regions on the other hand, and you will find that the green revolution also reached a plateau in the late 1970s and early 1980s that we had to make a transition from the green revolution to the genetic revolution, gene revolution. Okay, in the green revolution what we generally found that that the transfer of genes within the species, and in the gene revolution the transfer of genes across the species. Okay, and in the context of genetic manipulation of plants, what we have seen that when the state was the sole sponsor of scientific research, the state was the owner of seeds, hybrid seeds promulgated by the green revolution. Now the multinational corporations have become the owners of such genetic revolution, where we understand life, we understand plants at a molecular level, at the level of genes. Okay, and such transition from green revolution to gene revolution has significant implications for the questions of ownership over seed, control over seed. Now the farming community doesn't have the ownership over their seeds, which they have been using, exchanging for generations, across generations. Now the MNCs, multinational corporations, they have taken over. Okay, if you look at these changes, that the society will not be suddenly surprised by such crisis point, because we have made this transition. You look at BT cotton, BT brinjal, proprietary non-food crop controversy, BT cotton, proprietary food crop controversy, BT brinjal, Bacillus thuringiensis cotton, Bacillus thuringiensis brinjal and so on. That such if one, when we enter the crisis point, that perhaps the society will not be very surprised, at which the amount of land needed becomes greater than available. Symptoms of the crisis would begin to appear long before the crisis point is reached, and food prices would have risen to so high that some people would are starving now. Others are forced to decrease the effective amount of land they use and shift to lower quality diets. These symptoms are already apparent in many parts of the world, including India. Although only half of the land is now under cultivation, perhaps you will what we are witnessing, that death related to poverty, starvation, malnutrition each year, which can be attributed directly or indirectly to the public policies of the state. And there is no question that many of these deaths are due to the world's social limitations rather than its physical ones. Yet there is a clear link between these two kinds of limitations in the food producing system. If good fertile land were still easily reached and brought under cultivation, there would be no economic barrier to feeding the hungry and no difficult social choices to make. The best half of the world's potentially arable land is already cultivated. However, and opening new land is already so costly that society has judged it uneconomic. And this is a social problem exacerbated by a physical limitation. Even if society decides to pay the necessary costs to gain new land or to increase productivity of the land already cultivated, then it shows how quickly rising population would bring about another crisis point. And each successive crisis point would cost more to overcome. Each doubling of yield from the land would be more expensive than the last one. And we might call this phenomenon the law of increasing costs. The best and most sobering example of that law comes from an assessment of the cost of past agricultural gains. How many people can be fed on this earth? There is of course no simple answer to this question that the authors of the LTG felt. The answer depends on the choices that the society makes amongst various available alternatives. There is a direct trade-off between producing more food and producing other goods and services needed or desired by mankind. The demand for these other goods and services is also increasing as population grows, and therefore the trade-off becomes continuously more apparent and more difficult to resolve. Even if the choice were consistently to produce food as the first priority, nevertheless continued population growth and the law of increasing costs could rapidly drive the system to the point where all available resources were devoted to producing food, leaving no further possibility of expansion. Then what is important, that what we have discussed so far as food production is concerned, for example, that this is only one possible limit of food production, may be arable land. There are other possible limits, but space, I mean, if you look at this, there are many other possible points. I can tell you that look at the public policy which perhaps doesn't help the hungry, help the poor. I mean, public policies do not help us take a tour out of poverty, take a journey towards no death due to starvation, no death due to malnutrition, no death due to hunger, and so on. I think we must understand the nature of the state within the matrix of a class divided society on the basis of the kind of divisions that we tend to witness on the basis of caste, on the basis of class, on the basis of gender, on the basis of ethnicity, on the questions of citizenship, on the question of nationality, and so on. Okay. The another limit may be the availability of water and so on. If you for example, if you look at the non-renewable resources, I mean consumption of non-renewable natural resources, I mean how resources get depleted and so on. Even taking into account such economic factors as increased prices with decreasing availability, it would appear at present that the quantities of platinum, gold, zinc and lead are not sufficient to meet demands. At the present rate of expansion, silver, tin, uranium may be in short supply even at higher prices by the turn of in the 21st century. Maybe what the authors of LTG thought that maybe by the year 2050, several more minerals may be exhausted if the current rate of consumption continues. Despite spectacular recent discoveries, there are only a limited number of places left to search for most minerals. Geologists disagree about the prospects for finding large new rich ore deposits. Reliance on such discoveries would seem unwise in the long term. That's what the authors of LTG suggest. If you look at the non-renewable natural resources, and the authors of LTG, they looked at aluminium, chromium, coal, cobalt, copper, gold, iron, lead, manganese, mercury, and so on in different countries, in different continents. Okay, petroleum and so on, silver, gold, and so on in different countries. Okay, that's extremely important to understand the world's known reserves. That's what we discussed, how the world's known reserves, maybe chromium, for example. That's what we discussed, how the amount of chromium reserves was 775 million metric tons in 1972, of which 1.85 million metric tons were mined annually. And if the at the current rate of use, the known reserves would last about 420 years. The actual world consumption of chromium is increasing, however, at the rate of 2.6% annually. And if you look at this, if it continues, then perhaps chromium would deplete the resource stock, not in 420 years, but in just 95 years. If we suppose that reserves yet undiscovered could increase present known reserves by a factor of 5, that's what we have discussed, then this 5-fold increase would extend the lifeline of the reserves only from 95 to 154 years. Even if it were possible from 1970 onward to recycle 100% of the chromium so that none of the initial reserves were lost, the demand would exceed the supply in 235 years. Okay, that's why we might define a new index, that's exponential reserve index, which gives the probable lifetime of each resource, assuming that the current growth rate in consumption would continue. Okay, that's why the authors of the LTG thesis calculated an exponential index on the assumption that our present known reserves of each resource can be expanded 5-fold by new discoveries and so on. Okay. Of course, the actual non-renewable resource availability in the next few decades would be determined by factors much more complicated than can be expressed by either the simple static reserve index or the exponential reserve index, and this problem with a detailed model that takes into account the many interrelationships among such factors as varying grades of ore, production costs, capital costs, new mining technology, the elasticity of consumer demand and substitution of other resources. Okay. If you look at William W. Behrens the third, who was one of the authors of the LTG thesis, he was trying to look at these factors, namely the grades of varying grades of ore, production costs, new mining technology, the elasticity of consumer demand, and the substitution of other resources. Okay. At first, I mean that one must understand that the amount of reserves remaining, I mean labeled reserves, and the amount used each year, that is usage rate of usage, and the extraction cost per unit of resource, I mean actual cost, the advance of mining processing technology, and the fraction of original use of the resource that has been shifted to a substitute resource. At first, the annual consumption of chromium grows exponentially and the stock of the resource is rapidly depleted. The price of chromium remains low and constant because new developments in mining technology allow efficient use of lower and lower grades of ore. As demand continues to increase, nevertheless, the advancement of technology is not as fast enough to counteract the rising costs of discovery, extraction, processing, and distribution. And price begins to rise slowly at first and then very rapidly. The higher price causes consumers to use chromium more efficiently and substitute other metals for chromium whenever possible. Perhaps you will, what the authors of the LTG thesis claim that perhaps after 125 years, the remaining chromium, about 5% of the original supply, is available only at prohibitively high cost, and mining of new supplies has fallen especially to zero. The more realistic dynamic assumption about the future use of chromium yields a probable lifetime of 125 years, which is considerably shorter than the lifetime calculated from the static consumption of around 418 years, 420 years, but longer than the lifetime calculated from the consumption of constant exponential growth, that is 93 years or 95 years. The usage rate in the dynamic model is neither constant nor continuously increasing, but bell-shaped, I mean with a growth phase and a phase of decline. One must understand that the effect of a discovery in 1970 that doubles the remaining known chromium reserves, the static reserve index in 1970 becomes 800 years instead of 400. As a result of this discovery, costs remain low somewhat longer, so that exponential growth continue longer than it was expected. It was anticipated. The period during which use of the resource is economically feasible is increased from 125 years to 145 years. In other words, a doubling of the reserves increases the actual period of use by only 20 years. The planets, I mean the Earth's crust contains vast amounts of those raw materials which human beings have learned to mine and to transform into useful things. However, vast those amounts may be, they are not infinite. They are finite natural resources. That's why non-renewable natural resources. Now that we have seen how suddenly an exponentially growing quantity approaches a fixed upper limit, what the authors of LTG suggested that given the present resource consumption rates and the projected increase in the rates, the great majority of the currently important non-renewable resources would be extremely costly 100 years from now. Okay, such statement remains true regardless of the most optimistic assumptions about undiscovered reserves, technological advances, substitution and or recycling, as long as the demand for resources continues to grow exponentially. The prices of those resources with the shortest static reserve indices have already begun to increase. The price of mercury, for example, has gone up 500%, that's what in the last 20 years, and the price of lead has increased 300% in the last 30 years. The simple conclusions that the authors of LTG thesis have drawn by considering the total world reserves of resources are further complicated by the fact that neither resource reserves nor resource consumption are distributed evenly about the globe. If you look at this, that I mean, if you look at such conclusions that the authors of LTG have inferred, have drawn, okay, it clearly shows that the industrialized consuming countries are heavily dependent on a network of international agreements with the producing countries for the supply of raw materials essential to their industrial base. Added to the difficult economic question of the fate of various industries as a resource after resource, becomes prohibitively expensive, is the imponderable political question of the relationships between producer and consumer nations as the remaining resources become concentrated in more limited geographical areas. And if you look at different countries, India is one of the examples. You can look at South American mines and successful Middle Eastern pressures to raise oil prices suggest that the political question may arise long before the ultimate economic one. Okay. So, what we have discussed in this lecture, we have discussed the background to the limits to growth. This is a report for the Club of Rome's project on the predicament of mankind. The Club of Rome, I mean the predicament of mankind, I mean humanistic architecture and participation of stakeholders in democratic dialogue. And then we have discussed what kind of methodology that the authors of the LTG thesis adopted, and what is the distinction between physical necessities and social necessities. Okay. Then how 5 variables, namely world population, industrialization, pollution, food production and consumption of non-renewable natural resources, I mean resource depletion, were examined in the original model of the LTG on the assumptions that exponential growth accurately described their patterns of increase, and that the ability of technology to increase the availability of resources only linearly. And there were 3 scenarios, I mean overshoot, collapse and it may lead to a stabilized world. And we have discussed exponential reserve index through this formula and commodity reserve extrapolation through different resources, maybe chromium, gold, iron, lead, petroleum and so on. But please remember one thing, that the static reserve numbers assume that the usage is constant and the exponential reserve assumes that the growth rate is constant. Both are flawed ones. Okay. And then we have discussed how the chapter 2 of LTG suggests that given present resource consumption rates and the projected increase in the rates, the great majority of the currently important non-renewable resources will be extremely costly 100 years from now. And we can see now how the prices of gold, prices of non-renewable natural resources are increasing by leaps and bounds. And that's how we have come to this point of the limits to growth with global industrial per capita, global food per capita, global services per capita, global population and so on, population capital ratio. And what we'll do in the next lecture, we'll complete this portion of the limits to growth thesis, and then we'll move on to from behavior modes of the population capital system. Behavior modes which refer to tendencies of the variables in the system. Maybe population, maybe pollution, maybe food production, maybe resource depletion, maybe industrialization, for example, to change as time progresses. And then we'll try to complete the limits to growth thesis, and then we'll move on to Small is Beautiful. But before moving on to Small is Beautiful by E.F. Schumacher, we'll try to complete this in the next lecture. This portion of the limits to growth thesis, a report for the Club of Rome's project on the predicament of mankind. Thank you.